So we're continuing with section 2.4, and we're trying to determine where a function is continuous or not. And so looking at this example 4, part 1, and looking at this example, I see it's the square root of a polynomial, so it's definitely it's an elementary function, so it's continuous on its domain. How do I find the domain though? Let's notice that the square root functions are only defined on values that are 0 and bigger than 0. And so we have to set x squared minus 2x minus 5 bigger than or equal to 0, and then solve, and it's an inequality of a quadratic form, therefore I have to find the zeros of it. First let's find the zeros. X equal to by quadratic equation 2 plus minus 4 minus 5 times 4, which is going to be plus 20 divided by 2. And so this is going to be 2 plus minus square root of 24 divided by 2. We can also simplify this, but let's keep it that way. And so in simplifying this is going to require taking a 4 outside the square, and it's going to be 2 square root of 6 divided by 2. So, and then factoring 2, 1 plus minus square root of 6 divided by 2, and you end up with 1 plus square root of 6. And so plus minus. The lower number is 1 minus square root of 6. The upper number is 1 plus square root of 6. And this is a quadratic function, therefore it's a parabola with the leading coefficient that is 1, therefore it looks upward, so it has to be positive over here and a negative value over here. So domain of this function is negative infinity and 1 minus square root of 6 union with 1 plus square root of 6 and infinity. And these two endpoints are included and the other two are not. And so the domain of function is here, and r of x is continuous on this domain. How about in part 2 of the example, which is f of x equal to x squared plus cosine of 2 to the power x plus 9 over x minus 8. And so in this case, cosine takes any value, any real number n, so that is not going to cause any restriction to the domain. And x squared also doesn't cause any restriction, but x minus 8 in the denominator, so the 0 of the denominator is a restriction to the domain. Again, the function is elementary because it's a finite number of compositions or plus minus times divide of the elementary functions, basically, and elementary functions that we know. And so that therefore, to find the domain, you just have to exclude 8 and negative infinity 8 union 8 8, and infinity is the domain, and the function is continuous on this domain. So how about this one? Again, an elementary function. It's just a composition or other function operation of over simple elementary functions. And so in here, the only thing that causes restriction is denominator and square root. So denominator cannot be 0, and under the square root has to be positive. So together it means that this has to be positive, or under square root has to be bigger than or equal to 0, but the denominator cannot be 0, so it has to be bigger than 0. I'm sorry, I said under square root has to be positive, bigger than 0, bigger than or equal to 0. And so, and here that means that x is bigger than -5. That's -5, and infinity is the domain, and h is continuous on this domain. So how about part 4 of the example, e to the power tangent of x over x. So here I immediately see that x equal to 0 cannot be included. Also, anywhere the tangent of x is not continuous, is not defined, is not included in the domain of this function. And so basically function is not continuous at x equal to 0, and at all x's that are equal to pi half, where cosine is 0, cosine of x is 0, plus k pi. So if you exclude all those, function g is going to be continuous on this. G is continuous on this domain without when you exclude all of those, which will be infinitely many intervals. So the next question is next example 5 is find the value of c that will make the function continuous at x equal to 3. So just looking at this, and c is a constant, right? Looking at this function, it seems like this part is one piece of this piecewise defined function is a linear function. The other piece is a rational function. And rational functions are continuous on their domain, linear functions are continuous in the domain, but this function is restricting the domain of both of those pieces, basically. So each piece is continuous on its domain. That means that this piece has a discontinuity at x equal to 0, and this piece has no discontinuity on the interval 3 and infinity, not excluding 3, not including 3. And so what we're saying is that each piece is, but the part that they are pieced together may not be continuous. So when you have a piecewise defined function, you can find the domain of each piece and intersect it with the domain, the restriction of the piecewise defined, and that would be all continuous within that, and then you have to check the cutoff points where the two pieces are pieced together. So let's go to the link and watch both. So this actually gives you a little chance to look at the two pieces. One piece, remember, the first piece to the left of 3 was piecewise defined, and it was a rational. To the left of the piecewise defined function, is a rational function, and then the other piece is a linear function. But the linear function has a constant that is c, and c can change, and so basically you can bring the linear line up or down, that little piece of the line up and down, and at some point I can't quite be precise, but at some point they become connected to each other. So we're trying to find that point that it becomes connected, and I can't quite, we have to make this a little bigger and make sure that that we're finding the right number, but it's approximately around 21 that is happening. So let's make sure that that's the value actually. So that's what we're doing. We're finding that C that connects these two pieces together, but we're explaining this in mathematical terms. And so back to here, and we're trying to basically find the value of C that makes these two be connected together, right? And what does that mean? That means that prediction that we're coming from right side and prediction that we're coming from the left side are equal to each other, equal to the value of the function. What is the value of the function? It uses the left values, left piece of the function, and so basically f at 3 is equal to 2 times 3 plus 9 over 3, which is 6 plus 3, 9. Now, what in the other part is that I have to find limits as x approaches 3 from left side. What is to the left of 3? That would be this piece. So I'm finding that. Again, this is a continuous function, so I can basically plug in 3 into here. It's continuous at 3, so I can plug in 3 to find the limit. And so that would be equal to 9. And then the limit from the right side is, I have to use the piece that is to the right side of 3. That's x values are bigger than 3. So I have to find the limit of this. And again, this is a continuous function, so the limit within its domain is on its domain, so limit of any, as x approaches any value within its domain, is just plug in. Negative 4 times 3 plus c. And that is negative 12 plus c. So this value should be equal to this value, equal to that value. In this case, these two are equal, so I don't have to worry about that. And so I just have to set 9 is equal to negative 12 plus c, and solve to get c equal to 21. So c equal to 21, when we watched it on the app, that they actually, the two pieces are connected together if c is equal to 21. And this is what we get from the definition of the continuity as well. So if we want continuous at x equal to 3, that's the value that we have to use basically. And then for c equal to 21, the function is continuous everywhere but at x equal to 0. Example 6. Classify the discontinuity of the function f of x equal to x squared minus 16 over x minus 4 for x not equal to 4. 10 for x equal to 4. So what we not need to do is, first of all, check the discontinuity of each piece. Well, this piece is only 1 point, so you don't have to. But this piece has a domain. Within its domain, x squared minus, and the domain, so within its domain, y equal to x squared minus 16 over x minus 4 is continuous. Why? Because I can simplify this within its domain. That means x not equal to 4. It's going to be x minus 4 times x plus 4 divided by x minus 4. That is y equal to x plus 4. So within its domain, it's just the line. And therefore I can find, also I can find the limit. So what I need to do is also to find the limit at the cutoff. And for both limits, to the right and to the left of 4, I will have to basically use the same rule of the function, and that is 8. And so 8 is not equal to 10, which is f of 4 equal to 10. These two are not equal to each other. Therefore, the function is discontinuous. Discontinuous at x equal to 4. Now, note that even though it's discontinuous at x equal to 4, this function, if we had chosen the value of the function at 4 differently, namely if we had chose 8 instead, then this would have been continuous everywhere. This function would have been, or let's call this g of x, would have been continuous everywhere. So let's do iClicker question 2. Find the value. So far in this section, we've seen a lot of a method that if the function was elementary and within its domain, we actually plugged in the value of x equal to c as x, if x is basically if the limit is limit as x approaches c of f of x. And that's when we have continuity, we have this statement. This method is called direct substitution. This technique is called direct substitution. And it comes from the fact that we explain here. So this is one of the methods that we use very often to find the limits for elementary functions. Okay, so last section when we were just going through all the limit laws, we missed one. And so this is the one concerning the composition of the functions. We needed one little definition that came in this section. If f is continuous at limit of x approaching c of g of x, then limit x approaching c of f of g of x is equal to f of limit of x approaching c of g of x. And this is basically bringing the limit inside. That's something. If the continuity is true, you can bring the limit inside and no limit out there. Otherwise, you have to keep a limit outside, and we give you an example from the last section also on that one. And so, for example, in this case, I can bring the limit inside. First, I have to do one product, then bring the limit inside. And if I bring the limit inside the square root and inside tangent of x, what I get is under square root, I get square root of 1, and tangent of 0, and it would be